Hello everyone, section 11.2, areas of circles and sectors. Example 1, find each indicated measure, the area of a circle with a radius of 8.5 inches. So area equals pi r squared, 8.5 squared. Go to our calculator, and again we're going to use pi key on our calculator. 8.5 squared times, use the pi key, and I've got 226.98 inches squared. Part B, we want to go backwards. We know the area is 153.94 square feet. Our goal is to find the diameter. Still use the formula. Area equals pi r squared. Only this time we're putting the 153.94 into the area. 153.94 equals pi r squared. Divide by pi, r squared equals 153.94 over pi. Square root that, and that will get us the radius, and then we'll double that to find the diameter. So 153.94 divided by pi. Square root that, we're really close to 7, approximately 7 feet. I give you a formula to find population density. Find each indicated measure. About 124,000 people live in a 2-mile radius of a city's post office. Find the population density in people per square mile. So first we're going to have to find out how many square miles there are in a 2-mile radius, and we're going to take the number of people divided by the area of the land, and that will give us our population density. So area equals pi r squared. So 4 pi square miles, or miles squared, square miles. Okay, now we're going to take the number of people divided by the area, 124,000, divided by 4 pi, approximately 24 divided by 4 divided by, again use the pi key, approximately 9,868 people per square mile. A region with a 10-mile radius has a population density of 869 people per square mile. Find the number of people who live in the region. So now I'm giving you the population density. We're going to calculate the area. We'll find the number of people. So to find the number of people, we're going to multiply population density by the area. Will give us the number of people. So let's find the area first. Area equals pi r squared, 100 pi square miles. Is our area, and we want to take that area and multiply it times our population density, 869 people. So number of people equals 869 times 100 pi. 869 times times 100 times the pi key is approximately 273,004 people. Since we're dealing with people, let's round it to the nearest person. We don't want to have fractions of a person. Alright. Example 3. Example 3 is dealing with a sector of a circle. Sector of a circle is analogous to arc length. Arc length was a fraction of a circle's circumference. A sector of a circle is a fraction of the circle's area. Okay? So again, we can use either the ratio, the proportion setup, or the formula setup, either one. Find the area of the sector formed by angle PSQ. That's this angle here. So 135 degrees is the area of sector PSQ is equal to 135 divided by 360. That's what fraction of the circle we have, times pi 15 squared. So 135 divided by 360 times pi times 225, which is 15 squared, gives us approximately 265.07 square centimeters. Example 4. Same circle, same sector. This time I'm telling you the area of the sector. We want to figure out the area of the entire circle. Okay? So the area of sector PSQ over area of circle S is equal to 135 over 360. I'm using the proportion setup this time. 48 is going to go into here. 48 over area of circle S equals 135 over 360. Cross multiply. 135 area of circle S equals 48 times 360, 17,280 divided by 135. So the area of circle S is equal to 128 square feet. Here's example 4. Example 5 is this composite shape. Okay, a farmer has a field and the shape shown kind of looks like a heart. Find the area of the shaded region to the nearest square meter. So here we have a semicircle, another semicircle, and a square. Okay. So the area of the two semicircles together is the area of one circle added to the area of the square. So the radius of this semicircle is 4 meters. So the area of the circle is equal to 16 pi. Area of the square is equal to 64. I should label meters squared. So the area of the heart shape is equal to 64 plus 16 pi meters squared, or approximately 16 times pi plus 64, 114.27 meters squared. And depending on the directions, you're going to give one of these two answers. Example 6. We're going to fill out this chart. Depending on what the given information is, we can find all the missing information. Okay? But we're going to leave our answers in terms of pi. If the radius is 11, the diameter is 22. If the diameter is 6, the radius is 3. If the diameter is 22, the circumference is 22 pi. If it's 6, then it's 6 pi. If the diameter is 22, then the area, if the radius is 11, then the area is 121 pi. If the radius is 3, then the area is 9 pi. If the circumference is 16 pi, then the diameter is 16. The radius is 8. If the radius is 8, then the area is 64 pi. If the area is 81 pi, then the radius is 9. Diameter is 18, and the circumference is 18 pi. This one's the only one that's a little bit tricky. If the area is 18 pi, then the radius is the square root of 18, which is 3 square root of 2. If the radius is 3 square root 2, then the diameter is 6 square root 2. If the diameter is 6 square root 2, then the circumference is 6 pi square root 2. That was the only one that was a little tricky. Example 7. Sector AOB is described by giving the angle AOB. So we're going to be told what the different angle is for angle AOB, and we're going to have different radii for a circle O. We're going to find the length of the arc AB and the area of the sector AOB. We're going to leave our answers in terms of pi. So basically what this is an exercise in saying, well, all right, what fraction of the circle are we dealing with? And what's the circumference? What's the area? And let's apply the fraction of the to the circumference and the fraction to the area. So what fraction of the circle are we dealing with here? It's 1/4 of the circle. This is 1/6 of the circle. 360, this is 1/12 of the circle. 1/8 of the circle. 1/3 of the circle. 240 doesn't reduce down to quite as nice as this, but it's not bad. 240 over 360 is 24 over 36. They both reduce by 12. 2/3 of the circle. 1/2 of the circle is a nice easy one. 3/4 of the circle, 270 over 360. 40 over 360. 40 over 360, the zeros cancel. 4 over 60. 4 over 36, which is 1/9. 320 over 360 is 32 over 36. They both reduce down by 2, giving us 16 over 18, which is going to reduce down again. Let's see, 32 over 36. They both reduce down by 4. So we get 8 over 9, sorry. 8/9. 108 over 360. You know what? I'm just going to leave it as 108 over 360. I know it reduces. I'm going to leave it. 20 over 360 is going to be 20 over 36, or 10 over 18. Let's see, 4, 5. ninths. Okay. Circumference. If the radius 10, the circumference is 20 pi. 1/4 of 20 pi. So 1/4 of 20 is 5 pi. Area is 100 pi. 1/4 of 100 is 25 pi. The radius is 12. The circumference is 24 pi. 1/6 of 24 pi. 4 pi. The radius is 12. The area is 144 pi. 1/6 of 144. Pulling out my calculator. So 144 divided by 6, 24 pi. The radius is 12. The area again is 24. 1/12 of 24 is 2 pi. The area again is 144. 1/12 of 144 is 12 pi. Alright, the radius is 4. The circumference is 8 pi. 1/8 of 8 pi is pi. 16 pi is our area. 1/8 of 16 pi is 2 pi. Circumference is 6 pi. 1/3 of 6 pi is 2 pi. 9 pi is the area. 1/3 of 9 pi is 3 pi. 2/3 of 6 pi is 4 pi. And 2/3 of 9 pi is 6 pi. Radius is 5. The circumference is 10 pi. Half of that is 5 pi. Area is 25 pi. Half of that is 25 pi over 2. You could write 12.5 pi, but I like 25 pi over 2. Circumference is 16 pi. 3/4 of 16 is 12 pi. 64 pi is the area. 64 divided by 4 times 3 is 48 pi. Circumference is 12 pi. 1/9 of 12 pi is 12 pi over 9, which reduces to 4 pi over 3. 36 pi is our area. 1/9 of 36 pi is 4 pi. Here, 8/9. 8/9 of 12 pi. Just making sure that I got that right. So 12 times 8 is 96 divided by 9. Doesn't divide evenly, but it's going to reduce. Let's see. We have 96 pi over 9, and they both reduce by 3. So we have 32 pi over 3. 36 pi. Oh, I could take this one times 8. 4 pi times 8 is 32 pi. 4 pi times 8, again 32 pi. Quicker. 25 is the radius, so the circumference is 50 pi. 50 times 108 divided by 360 is 15 pi. 625 is our area. 625 pi. 625 times 8 divided by 360. Oh, it doesn't divide evenly, but I'm going to leave the decimal this time. 187.5 pi. It's just a little bit quicker to write it that way. Here we have 5/9. No, I can't go back to that one. Well, I could adapt, but the circumference is 6 pi. 6 pi is 30 pi over 9. That reduces down to 10 pi over 3. The area is 9 pi times 5/9 is 5 pi. That was example 7. Example 8. ABCD is a square with side length S. Square, square, right angles here as well. The arcs are drawn with a radius of S, so arc DB this way and arc DB this way. Both are arcs of a circle. They're both 90-degree arcs with a radius S. Find the area of the square, S squared. Find the area of sector BCD. So BCD, we're going to find this whole sector. Okay? Well, that's 1/4 the area of the circle with a radius S. So area of circle C, with radius S, is equal to S squared pi, or pi S squared. And we want 1/4 of that because that's this area, this sector. So pi S squared over 4. And we want to find the area enclosed by the arcs. So we're going to find the white, the unshaded region. Okay, the unshaded region here. So we're going to take this area of the square and subtract from it the area of the sector that we just found. That's going to give me this shaded region. Okay, so the shaded region is equal to S squared minus 2 of the, minus pi S squared over 4. And I have to double that because that's this one and this one. Okay, so we have 2s squared minus pi S squared over 2. And now we want to, let's get a common denominator here. So I have 4s squared minus pi S squared over 2. This is the area of the shaded. I'm looking for the area of the unshaded. So I'm going to subtract this from the area of the square. Okay, so over here on the side, I'm going to go S squared minus 4s squared minus pi S squared over 2. Common denominator, 2s squared minus 4s squared minus plus, it now becomes plus. I just distribute pi S squared all over 2. And I'm going to rewrite this so that we have a positive in the front. The final answer is going to be pi S squared minus 2s squared, combine these like terms, 2s squared minus 4s squared, all over 2. Example 9. Example 9 is actually going to help us when we go to do example 11 in a little bit. So we're going to do example 9 first. In triangle ABC is equilateral. with side length S. Also tells us that this is 60, 60, 60. It's important in helping us later. Arc AB is it has a radius of S, the center C. Okay. Find the area of triangle ABC. So let's do that. We need height. We already know the base is S. This is 30. This is now S over 2, because we've cut it in half. And because it's a 30, 60, 90, this is now S square root 3 over 2. There's the height, the area of a triangle. Triangle ABC is equal to 1/2 base S over 2. No, I'm sorry, just S. Getting myself confused. Times the height, which is S root 3 over 2. So our final area of the triangle is S squared root 3 over 4. Find the area of the sector ABC. So that's going to be a fraction of the circle. So the area of circle C is equal to pi r squared, or pi s squared. 60 degrees is 1/6 of that circle. So the area of the sector is pi s squared over 6. And then we want to find the area enclosed by the arc AB and segment AB, this shaded region here. This is called in geometry textbooks a segment of a circle. Trigonometry textbooks are going to call it the same thing. So this piece here, the shaded piece, is called a segment of a circle. It's kind of like the crust of a piece of pizza, but it's not, because crust is an inner circle, or an outer circle, it's a concentric circle. This is a segment and an arc forming this region. To find the area of this, we take the area of the sector and subtract the area of the triangle. Area of the sector minus the area of the triangle. So pi s squared over 6 minus s squared root 3 over 4. Sorry, these are, if we want to get a common denominator of 12, we can. We don't have to. This answer is fine. If we get a common denominator of 12, we're going to get 2 pi s squared minus 3 s squared root 3 all over 12, if we wanted to. Final answer. This is units squared, units squared, units squared, and I should have put those up here as well. Units squared, units squared, units squared. Okay. My pencil. Example 10. Find the area of each shaded region in terms of pi. Point O marks the center of the circle. Okay. I don't need to have the center of the circle because I know that this has to be a diameter because it's a right angle. The other thing I know is this is a 5 because the Pythagorean triples, 3, 4, 5. And so the diameter is 5, making the radius 2.5. Okay, we want to find the area of the circle and then divide it by 2. So the area of the circle is equal to 2.5 squared pi, or 6.25. and the area of the shaded is equal to 6.25 pi over 2 units squared. Now, on example 10, one way to do this problem is to find the area of this unshaded region and subtract it from the area of the whole circle. Nothing wrong with doing that. I found that it's a little bit quicker to do this. Find the area of this triangle and add it to the area of 3/4 of the circle. So 4 and a 4. Area of the circle is equal to 64 pi. Area of the triangle is equal to 1/2 base times height, or 8. And 3/4 of 64, so 64 divided by 4 times 3 is 48. So we're going to take 48 pi plus the 8. So the area of the shaded is equal to 8 plus 48 pi units squared. Okay. Problem, the next one, I guess C. We could find the area of this segment of the circle and the area of this segment of the circle and add them together. Again, it's easier to find the area of the unshaded semicircle, the unshaded triangle, and subtract that from the area of the whole circle. It's just a little bit quicker. So again, I could, drawing the radius here, figure out this angle, right? I know this is 90 up here, so I know this has to be 30, and I could find all those angles. I could find the measure of the central angle here and find what fraction of the circle it is, find the area of this small triangle, subtract it from the area of this sector of the circle to get the segment of the circle. Do the same thing here, find this angle, find the area of this triangle, subtract it from the area of this sector of the circle to get the area of this segment of the circle, and then add these two together. It's quicker to say the area of the circle is 36 pi, because the radius is 6. Okay. So the area of the semicircle is going to be 18 pi. And then the area of the triangle. So again, this has to be a right angle here. This is 12. So this is 6. And this is 6 square root 3. So the area of the triangle is equal to 1/2 base times height. So 1/2 of 6 is 3. 18 square root 3. Area of the shaded is equal to 18 pi plus 18 square root 3 units squared. You could factor out the 18 if you want to and go 18 times pi square root plus square root 3 units squared. Either way. All right. Last one in this example 10. Again, multiple ways that we could do this. Okay, and I've done it a bunch of different ways. I have done it, the center's here. I've done it where I found this triangle times 2, and then this sector times 2. And I think I'm going to do that again. Okay. Again, there's more than one way to do this. I could just find the area of the unshaded times 2 and subtract it from the area of the whole circle. In this case, I think the two different methods are exactly the same amount of work. Okay. So this is 120, so this is 60 degrees here. From here to here. 30. This is 1. This is square root 3. So the 2 square root 3. So the area of the triangle, 1/2 base times the height, which is 1. So it's going to be square root 3. But we have 2 of them. We have 2 of these triangles. It's 2 square roots of 3. This is 60 degrees, which is 1/6 of the whole circle, but we have 2 of them. So we really have 2/6 or 1/3 of the whole circle. So the area of the circle is, if this is 1, then the radius is also 2. 30, 60, 90. Short side's 1, the hypotenuse is 2. So the area of the circle is 4 pi. And when I say 1/3 of 4 pi is 4/3. So we really have 4 pi over 3. And we're going to add that to the 2 radical 3. So the area of the shaded is equal to 4 pi over 3 plus 2 square root 3 units squared. And if you want to get common denominator, you can. You don't have to. All right, number 11. Like I said, number 11, we're going to use what we did on problem number 8 to answer problem number 11. To do that, this figure is created by a whole bunch of different arcs. So this arc here is part of a semicircle. Oh, it's part of a circle. This is another part of the circle. Okay. This I take right here. Shade this part. This is exactly the same as this segment. Okay? Radius of the circle is 6. So this is 6. That radius there is 6. Okay? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of these segments of a circle. Okay? So to find the area of one of the segments of a circle, we actually have a formula. 2 pi s squared minus 3s squared root 3 over 12. And we happen to be timesing by 12 because there are 12 of them. So for this problem, we're going to use 12 times 2 pi s squared minus 3 s squared root 3 over 12. So really it's 2 pi s squared minus 3 s squared root 3, and s is 6. 36 times 2, 72 pi, minus 36 times 3, 108 root 3 units squared. I can go through the whole process of finding this again, but I did it already in problem number 9. I'm not going to redo work that I've already done. Working smarter, not harder. Okay. Example 12. Which is a better buy? 10-inch diameter pizza costing $4 or 15-inch pizza costing $7? Okay. So if it's a 10-inch diameter pizza, then what's the area of the 10-inch pizza? The radius is 5, the area is 25 pi. And that costs $4. Okay. Area of the 15-inch pizza gives us a radius of 7.5, and 7.5 squared is 56.25 pi, and that cost $7. So which is the better buy? Okay. So 25 pi for $4 or 56.25 pi for $7. 25 divided by 4, 6.25 pi per dollar, and 56.25 divided by 7 is 8.04 pi per dollar. I'm getting more pizza per dollar in the 15-inch than I was in the 10-inch. So which is the better buy? 15-inch pizza. All right, example 13 is an actual coupon that I got a long time ago. I wish I still had the coupon, but I don't. And it had this deal on it. So which deal is better? 2 10-inch pizzas for $9.99 or 1 16-inch pizza for the same price of $9.99. So what this really comes down to, since the price for the two deals is the same, it comes down to which gives you more pizza. And they did this on purpose because people think that they're getting 20 inches of pizza here and 16 inches of pizza here, so this must be the better deal. They didn't do the actual math. What's the area of one 10-inch pizza? Well, we just did it, 25 pi. So the area of two 10-inch pizzas, area of two 10-inch pizzas, is going to be equal to 50 pi inches squared. And the area of the one 16-inch pizza, surprisingly, is equal to 64 pi inches squared. I'm getting 14 pi inches squared more, so 14 times pi. I'm getting almost 44 square inches more pizza with the second deal. That's like a 6.5 inch by 6.5 inch square amount of pizza for the same price. So what's the better deal? 16 pi inch pizza in this problem was the better deal. Number 14. A circular archery target has a 2-foot diameter. It's yellow, except for the red bullseye at the center, which is a 6-inch diameter. Find the area of the yellow region around the area to the nearest whole number. We're going to do this whole thing in inches. I could do it all in feet, but I'm choosing to do it all in inches. So a 2-foot diameter is really a 24-inch diameter or a 12-inch radius, giving me an area of the big circle equal to 144 pi inches squared. 6-inch diameter is a 3-inch radius. The area of the bullseye, is equal to 9 pi inches squared. So the area of the yellow is equal to 144 minus 9, 135 pi inches squared. And we want to round this to the nearest whole number. So 424 square inches or inches squared. Problem number 14. Problem number 15, find the area of sector ACB. Leave your answer in terms of pi. So we have an area of the whole circle is 36 pi, and we have a 100-degree angle, an arc. So that's going to be 100 over 360, 10 over 36, 5 over 18. So the area of sector ACB is equal to 100 over 360 times 36 pi. 36 and 360 reduce. 36 from 360 reduce down to 10. 10 reduces into 100. 10 pi meters squared. Example 16. Again, we're finding the area of the shaded region. This time it's a segment of a circle. So we have to find the area of the sector, the area of the triangle, subtract the area of the triangle from the area of the sector, and we'll be left with the area of the segment of the circle. So let's find the area of the sector. Which is equal to 120 over 360, 1/3, times the area, which is 24 squared pi. 24 squared is 576, and 1/3 of that is 192 pi feet squared. So that's the area of the sector. The area of the triangle equal to, so draw in the altitude here, making these 60, 60, 30, 30. Okay. That makes the hypotenuse 24, short leg 12, the long leg 12 square root 3, making this whole thing 24 square root 3 feet. So 1/2 base 24 square root 3, height 12, giving us 144 square root 3 square feet. We subtract the triangle from the sector, so the area of the shaded segment of the circle. 192, oops, 192 pi minus 144 square root 3 square feet. And we want to round to the nearest tenth. So we go to our calculators. 192 times pi minus 144 times square root of 3, giving me 353.8 square feet. Marine biology, example 17. A diver. The diver in the diagram below is working on bringing up samples of organisms from the ocean floor. The line in the diver to the diver is 100 feet long. So his air line is 100 feet long. The diver is working at a depth of 80 feet down to the ocean floor. What is the area of the circle that the diver can cover? So you want to think of this as like a cone being formed by the diver's air hose, keeping the diver in that circle. Now they can go inside the circle, but they can't go outside of that circle because the air hose wouldn't let them, right? So we need to know the area of the circle. To know the area of the circle, we need to know the radius of the circle. To know the radius of the circle, we need to know the Pythagorean theorem, specifically Pythagorean triples. This is 60-foot radius because it's a 60, 80, 100, so 3, 4, 5 Pythagorean triple. So if the area of the circle is going to be 60 square root 3,600 pi feet squared. We want to round to the nearest square foot times pi key, 11,310 square feet. And problem number 18, recreation. So an 8-foot by 10-foot floating dock. So we have 8 feet and 10 feet is anchored in the middle of the pond. The bow of the canoe is tied to the corner of the dock with a 10-foot rope. So this rope is 10 feet. I don't know if that's showing up. I think it'll show up if I use the pen. Maybe not. No, that shows up. Good. So, sketch the diagram of the region in which the bow of the canoe can travel. So, a little bit tricky. Here's our dock. This is 10 feet. That's 8 feet. When the canoe is, so the canoe is anchored here. When the canoe is here, that is the whole rope, 10 feet. It's going to go around in a circle, right? Because the rope keeps the canoe within 10 feet of the dock until it gets to here. And I probably should have been a little more careful, but that's all right. Because when it gets to here, now the rope stops here. 8 and 2, and now I get a different semicircle that only has a radius of 2. So for 3/4 of the circle, the radius is 10. For 1/4 of the circle, the radius is 2. Our plan for finding the area. It's exactly that. 3/4 of a 10-foot radius circle added to one quarter of a 2-foot radius circle. That's my plan. Well, let's actually do it. So the area of the 10-foot circle is going to be 100 pi. 3/4 of that is 75 pi. Area of the 2-foot radius circle is 4 pi. 1/4 of that is equal to pi. Add these together. 76 pi, and what do we got? Feet squared, and we will round to the nearest foot, so 76 times pi is approximately 239 square feet. That's our last problem. Thank you very much. Bye.